Okay, everyone, good afternoon. Welcome to our 13th and final lecture for the Postgraduate Dynamics course MSD 780. Today we're going to wrap up our fourth study theme, Integration of Optimization with DAP-BC. We're going to look at a second optimization example where we use DAP-BC to obtain our post-processing results and then optimize some sort of an objective function. But before we jump into that, I just want to give you a brief review of everything that we've done up to now in the Postgraduate Dynamics course, and just to sort of take everything together of how we moved between the study themes. So starting off with study theme 1, we looked at an introduction to planar multibody dynamics. And the focus over there was on the analysis and formulation that we apply to planar multibody mechanisms. We mentioned some compliance elements as well, so springs and dampers and actuators that we can have in a system. But most importantly, we considered the kinematic joints, which is the connectivity that we have between the different bodies of a system. So some of those examples were revolute joints. We also looked at disk joints, translational joints, all those kind of joints that enforce some sort of a constraint. So something that removes the degrees of freedom of your system. And we need those elements in our system to ensure proper connectivity between the bodies. If the bodies aren't connected, then they're all going to move in their own manner and abruptly, not really in a reasonable manner in which we expect the system to move. So that then brought us to study theme 2, where we really fundamentalized everything that we learned in the introduction. And that is where we started to look at the PMD method of analyzing a very simple mechanism, and I don't even want to call it a multi-body mechanism because technically it's just a pendulum rod, so a single body mechanism, which was connected to ground via a revolute joint. But even with that very simple example, we saw that the equations that we need, the constraint equations, the Jacobians that we derive, all of those things are non-trivial. So we can imagine if we now start to increase the number of bodies in the system, that the complexity of our Jacobian is also going to increase, and the overall complexity of the computations are going to increase, which just further substantiates the need for some sort of a computational solver that we need. And that is where DAP-BC started to come into play. And we looked at the pendulum rod with regards to DAP-BC. So we considered a few different types of pendulum rods, either a forward dynamics, an inverse dynamics, or a combined dynamic approach that we wanted to solve. And we saw that DAP-BC is able to effectively solve these problems in a fairly low computation time, low performance that we need, or high performance, low computation time when we solve these type of problems. We then took it one step further and we jumped into study theme 3, which then focused on application examples. And in that case, we now started to expand on the number of bodies that we have in the system, but we also considered our compliance elements, springs and dampers. This was then done through the use of suspension systems. So we looked at the McPherson suspension system, the double A-arm or wishbone suspension system, and that gave us a good idea of how we can start looking at sort of quarter car models or vehicle dynamics if we're interested in vibrational effects. We also looked at some kart examples as well, so where we have some sort of an input torque or an input driver motor that is applied to one of the wheels, what will the effects be on the overall motion of the kart? And we also considered a few other examples. So one was a friction model that we considered at the hand of a conveyor belt, so a box that is moving on a conveyor belt and which is actuated through some sort of a spring. And lastly, we looked at an alternative approach to friction, which is contact. So in that case, we considered a falling rod that impacts the ground, and we had a few different contact models that we can consider over there. With all of that now in place, we said, well, if we have some sort of an application example, we now had all of the properties of the system given. But in reality, we're going to be expected to design some of these properties or to choose these properties to maximize some performance indicators within our multi-body mechanism. And that is where study theme 4 then started to look at the optimization using DAP-BC. So we use DAP-BC to obtain the post-processing results, something like the maximum speed or the maximum acceleration in the system. Or if you're interested in the dynamic version, you can look at torques and forces that you get out of the system. And now you can ask, well, can I maximize some of these properties based on other properties in the system. We looked at one of the examples over there. Today we're going to look at a fairly simple example for where we have a card that where we want to maximize some sort of a kinematic property related to the input torque or input loads. And that will also give us an idea of how we can go about defining the objective function and defining the design variables with any equality and inequality constraints. So the actual optimization was handled by the dynamic queue algorithm. So we just plugged in dynamic queue into DAP-BC. We obtained the post-processing results from DAP-BC, and then we're able to go one step further and just use dynamic queue, and it performs an iterative algorithm to solve the optimization. And then lastly, two of the guest lectures that were our previous two lectures that we had was then study theme 5 with regards to the multi-body dynamics using MSD Atoms. So MSD Atoms is a commercial multi-body dynamics software package. This is just to give you an idea of what you can expect when you go into industry or the commercial environment, or if you want to take your academics to a more robust version of multi-body dynamics. Now, this is not to say that whatever we learned about DAP-BC and the planar multi-body dynamics textbook is in vain. A lot of the properties that we learned over there and setting up our multi-body mechanisms can be translated to some of these commercial software packages such as MSD Atoms. We saw that if you want to connect certain points via revolute joints as well for the slider crank mechanism, which was one of the examples that we looked at over there, we saw that you still need to define markers, which is essentially the points that we defined in DAP-BC. So there is some connotation that you can make between programs like Atoms and DAP-BC to better understand just how you're going to set up your system. But with all of that being said, I'm then going to jump into study theme 4 again, which is optimization and dynamics. And now we can start looking at the second application example, which is going to be a fairly simple example. There's only two design variables that we're going to change, but we're going to look at section 6.2 in this case, which is a card subjected to an aerodynamic and torque load. Now, if we look back at lecture 8, we're going to focus on card D in this case. I just want to zoom in a bit over here. Okay, so we reconsider the card model given in lecture 8. In this case, we had three bodies. We had body 1, which is the main card body, and then we had bodies 2 and 3, which are the rear and front wheels respectively. We had a few points that we specified over there in order to accommodate the revolute joint between the card body and the wheels, and then we also defined a disc joint which acts between the ground and bodies 2 and 3. And this ensured that we had no slip conditions in the system, and also that we had a normal force acting on the wheels. Now, our forward dynamics problem, we propose a relation for the torque and measure the angular characteristics of the wheels and card body. We once again expand on this application by now considering a few design questions. So we can say, how would the maximum specified torque influence the acceleration of the body? And what is the influence of the aerodynamic drag coefficient on the speed of the card? And we can use these type of questions to now formulate a rather simple design problem. In this case, we can now say we want to maximize the acceleration of card body 1, subject to the torque applied to the rear wheel and the aerodynamic drag coefficient. I think in our example, we actually referred to it as the aerodynamic damping coefficient, but in essence, we can assume for this problem that it's one and the same. A few design considerations is that the maximum time of motion should be taken as 6 seconds. We want to use a reporting time step of 0.1 second. So this will give us 60 time steps in total, which should be sufficient for our optimization problem. The torque should not exceed 50 Newton meters, so we have an upper limit on the torque. I'm also going to apply a lower limit on the torque, which is going to be 10 Newton meters. But then we have an upper and a lower bound on the maximum torque that we want to specify in the system. The card should achieve a maximum allowable speed of 1.2 meters per second during its motion. Okay, so let's perhaps just look at this last point. So since we are working with a maximum allowable speed, We know that this is one of the properties that we're going to get after the post-processor of DAP-BC has run, and it needs to obtain a value of 1.2 meters per second. So since we have the maximum allowable speed, which is equal to 1.2 meters per second, we then equality constraint in the system. Just quickly looking back at our original formulation, since we talked about maximizing the acceleration of guard body 1, the property that we want to maximize will be the objective function, so that's the acceleration of the guard body, subject to the torque applied to the rear wheel. So this subject to is then going to give us our design variables. So torque applied to the rear wheel is our first design variable, and then the aerodynamic damping coefficient is going to be our second design variable that we want to impose on the system. Okay, so following the optimization procedure, we remember that we start by defining the objective function, and this we can do in the post-processor. Once again, remember the acceleration of guard body 1 is something that we get out from the post-processor. So within the post script, we need to go and define the maximum acceleration of guard body 1. So how do we do this? If I go over to Octave, then I can head to DAP-BC Dynamic Q Hybrid Workbench. And before I perhaps jump into post, I first want to go to dap.m and just make sure that I'm working with the correct model in this case. So if I scroll all the way up, zoom in a bit, let me just close all of these tabs at the top over here as well. Okay, so I start in line 14, add path formulation, that's fine, and then I have the input line that I've commented out. Now I need to give the actual folder of the model that I'm working in. So remember from over here, we said that we're working with guard_D. So I just need to make sure that my folder is also guard D in this case. Then the answer to the initial condition correction is still yes, so that's fine. Now I also need to set up my final time and my reporting time step. So after line 40, which has been commented out for the input, I just need to give line 41 as T final is equal to 6 seconds. So that's fine. And then in line 48, I also define dt as 0.1 seconds. And all of this information I got from the design considerations. Maximum time of 6 seconds, reporting time step of 0.1 seconds. Right, and then I just make sure that these two lines at the end are also commented out, 54 and 55, just so that I don't have to print out the function evaluations at each step. If I'm happy with that, now I can head over to post, and over here I'm going to define the maximum acceleration, which is my objective function. So if I scroll down to line 66, I can call this max ACC val, which is simply equal to, and let's first calculate for all time steps the acceleration. So it's just Pythagoras ax squared plus ay squared. So I'm just going to use the square root of rdd for all time steps. I'm working with body 1 because I'm interested in the cart's acceleration in the one direction, or the x direction, dot squared, so that I do element wise squaring over here, plus the acceleration for all time steps of body 1 in the 2 direction or in the y direction, dot squared. And I can just close it up for the square root. And since I'm interested in the maximum value, I'm just going to say, well, I'm going to extract the maximum value over here. So I just add max and the parentheses at the start and at the end as well. Okay, so now I've defined the maximum acceleration value. Now I can head to the second point over here, which is defining the design variables in the system. So remember that we're working with the torque applied to the rear wheel and the aerodynamic damping coefficient. So I'm going to say over here x1 is going to be the maximum torque and x2 is going to be the aerodynamic damping coefficient. Now I just need to go to step 3 and define these design variables in the corresponding DAP-BC input files. And in my case, this is then going to be under models. I'm considering part D in this case, so I'm expanding that. And both the aerodynamic damping coefficient and the maximum torque were defined under user force. So if I double click on user force, I can head in over here And in line 5, I have omega x is equal, or omega max is equal to 4 pi, but then I also say T max is equal to x dap 1. Now this, I believe, was a constant value in the script that you have available, so you just have to go and change this to x underscore dap 1. Remember that we're working with x dap in this case, since we're still busy with the dap BC input files. If there's anything that we have to change in the dap BC input files, we need to use x underscore dap to define our design variables in the script. So once this is done, I also just need to go and update the aerodynamic damping coefficient. In this case, it was given in line 15, so damp aero is now equal to x dap 2. And then I've now defined both of my design variables in accordance to the indexing that I used in step 2 over here. Once I'm happy with that, I just go to step 4 and I make sure that x dap, or a global definition. So to do that, I just head to formulation, I go to some files, and I open up include global. And you'll see over here in step 2, I have global x dap, so that's fine. That means that whatever my variables are that I define over here, it will be shared between the dap BC input files and between the dynamic Q optimization files. Then I can go over to step 5 as well, and this is now where I define the equality constraint pertaining to the speed. And remember that the speed is an implicit value that I get. I only get it after I've performed the post-processing or the actual dynamic analysis. So I can't go and directly define it under one of my dynamic Q input files. I need to first define the variable under my post-processor. Now to do that, I head to post over here, and you'll remember that I defined now maximum acceleration value. So next I just have to go and define the maximum speed value. So I'm just going to call this max speed val, which is now more or less the same as what I had in the previous point. So I'm just going to say Control C and Control V, but now I'm working with the speed. So it's just going to become RD instead of R double D. So now I've defined my implicit variable max speed val. So now I'm ready to go over to my minimizer inputs transition file, where I now specify all of the implicit values that I got from DAP-BC in order to relate them to the dynamic Q files. And if I do this, I then head over to minimizer inputs. Let's zoom in a bit. So everything above line 8, I'm going to leave as is. I just have to change the objective function and the equality constraint, which was implicitly defined. Let me just delete that. And now I can say the objective function is going to be equal to the maximum acceleration value. But remember that the question that I had over here was I want to maximize the acceleration of the body. But whenever I define some dynamic Q algorithm, I do a minimization if I set up the optimum design problem. So if I have a maximization problem, I can change it to a minimization problem by taking the objective function and multiplying it by -1. In my case, this is now simply going to be the maximum acceleration value multiplied by -1. And then I can also define my equality constraint, H1, which is then going to be the maximum speed value minus the value that was given over here, 1.20 meters per second. Okay, so those are the two implicit variable or implicit objective function and constraint definitions that I had. At the end, I just have to make sure that if I now have objective function over here and H1, that at the top for my function, I also have objective function and H1. If I now had a second, let's say, inequality constraint, so C1 is equal to some equation over here, I just have to add C1 over here as well, so that I can translate that value over to the dynamic Q workspace as well. Okay, but in our case, we don't have any inequality constraints defined on the system, so objective function in H1 is fine. Once I'm happy with this, then I go over to the next step, where I now delve into the dynamic queue workspace. So I just expand the dynamic queue folder, and I head over to fch.m, which is now where I have to go and define the objective function and also parameterize the constraints in the system. Okay, so in this case, you'll also see that I have objective function and h1, which is equal to the minimizer inputs x. It takes in all of the design variables and gives me the objective function and equality constraint out. And now I just have to go and define them in accordance with the fch.m file outputs that I need to give. So f, which is my objective function, c, inequality constraints, and h, the equality constraints. In my case, I'm then going to say f is simply this objective function that I extract over here, and then h parentheses 1 is the correct way to denote that I'm working with the first equality constraint, and that is simply equal to this variable h1 over here. Once I'm happy with that, I can just head over to grad fch, and I just have to make sure that I'm working with some sort of a finite difference method over here to find any gradients that I have in the system, and that I also have a suitable step size. So as mentioned, if we don't have a step size given to us, then we just use 10 to the negative 8. So 1.d minus 8 is 10 to the negative 8. It's a fine enough step size for the dynamic queue optimizer to give good results. And we can also see in this case we are now working with a backward difference method, since we have fd minus f. Okay, so that should be fine. And then the last step is just to go over to my optimization.m file that I have over here. And this is now where I have to specify any bounds that I have on the system. I start off with line 9 over here, which is then x1. So the initial conditions that I specify on each of my design variables. For x1, which is the maximum torque, I'm going to start with a value of 20 Newton meters. And then for x2, I'm going to start with a value of 5. And this was the aerodynamic damping coefficient that I specify. Then I just have to capture all of that within line 12. Since I'm only working with x1 and x2, so two design variables, my x0 list is going to contain only x1 and x2. Then I also specify the lower and upper bounds on any design variables. In my case, I said that I have a lower and an upper bound on the maximum torque of the system, so design variable 1, and that will be between 10 and 15 Newton meters. So I specify low as 1,10 and up as 1,50. Once I'm happy with that, I can just go over to line 18, where I now run the actual dynamic queue solver. So I give the initial conditions as the first input, the lower bound as the second input, upper bound as the third input, and then I have this value of 60, which is now the move limit. Up to now, we've only considered a move limit of 1. It was sufficient for the type of problems that we considered. But if we are interested in using larger move limits, we can reconsider the definition that we have for the move limits, and this is given in this guide DQ document over here. Okay, so if we scroll down to DML, which is the move limit, it says the move limit should be approximately the same order of magnitude as the radius of the region of interest, which is the square root of the number of design variables that I have n multiplied by the maximum variable range, which is so this is optional. If you don't specify the move limit, the default value of 1 is going to be used. But we can now go and calculate the move limit for our current problem, since we know what the variable range is on the maximum torque in the system. So to do this, I can go to edit, I just want to first update the font size over here. So let's perhaps do 14 just to make it a bit bigger. Okay, so if I calculate that, it's going to be the move limit should be equal to square root of the number of design variables that I have, so that is 2, multiplied by the maximum variable range. So my variable range is 50 Newton, or 10 to 50 Newton meters, so 50 minus 10. And if I hit enter, I get a move limit of 56.569. Since we're working in the same order of magnitude, we can now choose to round off this value. So we're simply going to use a move limit of 60. And that is where this 60 value comes from. Further than that, I'm just going to use some convergence tolerances on the system as well. So the default value of 10 to the negative 5 on the step size, and then 10 to the negative 5 on the objective function as well. And now I've fully set up my optimization problem, and I'm now ready to run the optimization and see what the outputs are going to be. Before I do that, I just type in over here, clear all, close all CLC, just to clear my workspace. And then I can type in optimization and hit enter. Right, so this is a bit of a simpler problem that we are considering, so it should run a bit faster than our previous problem that we had. I believe that the previous problem was, let me just check what that one was. The driven pendulum subjected to a constant torque. So we had quite a lot of acceleration variations in that system, which influenced the runtime. In this case, it's a bit of a simpler problem. We only have two very simple design variables that we are considering, so we expect it to run a bit faster. Okay, so looking at the results, we can see that in this case, we only needed 4 iterations to reach an optimization or an optimum value. If we look at the values, we can see that our final function value, or our acceleration value, is minus 4.03 meters per second squared. Our x norm is relatively high, it's about 0.3. So we actually converged on the RFD, or the residual of the objective function, which is 10 to the negative 10. X1 and X2 values are also given over here. So we have 50 Newton meters maximum torque, which will provide the maximum acceleration, combined with a 15.6 value on the aerodynamic damping coefficient. Now, if we look specifically at the maximum torque of the system, it does make sense that the higher the maximum torque rating of the motor is, the higher the acceleration is that I can reach in the system. Now, just looking at the final equality constraint values as well, we can see H1 in this case is 10 to the negative 6, or perhaps closer to 10 to the negative 5, but it's still a very small value, which gives us confidence in the fact that we were able to achieve a 1.2 meters per second maximum speed at the end. And then we also have final side constraints, which are both smaller than or equal to 0. So Cx1 is actually 0 in this case, and this just substantiates the fact that we are working with a 50 Newton meter maximum torque, which is the upper bound that we specified in the system. And in total, we only needed an optimization runtime of about 1 minute, which is not bad for this type of problem. If we just want to print out our optimized design variables, we can just type in X, and then we obtain these values over here for the maximum torque and for the aerodynamic damping coefficient. And at the end, we just have our objective function as well, which is minus 4.03. We just need to remember that we now performed a minimization on the acceleration. So we took our objective function, multiplied it by negative 1. Now, in fact, since we're working with an actual maximization problem, our actual maximized acceleration is going to be f multiplied by negative 1. And that then gives us the 4.03 meters per second squared value. Alright, so that is the results that we now obtained specifically from the dynamic Q optimizer. But now we need to go and do some post-processing as well. We'd like to look at what the graphs tell us about the kinematics of the system as well. So to do this, I can now simply say x dap is equal to x, and that now reloads the design variables into the DAP-BC domain. So now I have these results available, and I'm in a position to go and rerun DAP and post and see what happens to the results of the system. So if I type in DAP post, we can now see that the results have been generated. So now I just have to go and plot some of the results. So I'm first going to look at the acceleration of the system. So I can say, perhaps before I do that, we should just quickly run through the histories of the results as well. So let's perhaps first start with the objective function history. So this is just quickly back at the dynamic queue results that we got. These are all of the histories that were plotted once the dynamic queue was finished loading. Okay, so we see for our objective function, we started with a value of about minus 1.6 meters per second squared, and then we decreased the value. There's a bit of a kink over here at iteration 3, but then at iteration 4 we ended with our maximized acceleration, which was minus 4.03 meters per second squared. If we quickly look at the variable history as well, we can see that there's a bit of a variation at the start when we jump from 20 Newton meters to 50 Newton meters for our maximum torque. It remains there for 2 iterations, bit of a kink, and then we go back to our maximum value of 50 Newton meters. And then for X2, we can see a gradual increase in the aerodynamic damping coefficient up to the value of, I think it was 15.6 for that value. So the aerodynamic damping coefficient is perhaps more an indicator of the maximum speed of the system that was limited to 1.2 meters per second. And we're going to look at the graph in a moment of why this is important. So why we didn't make the damping coefficient 0 in order to maximize the acceleration. We needed to take into account the equality constraint and the 1.2 meters per second that we specify on the maximum speed of the kart as well. And then we just have the lower limit inequality constraint as well. So all of that is below 0, which is fine. If we then look at the upper limit inequality constraint history, we see that we start at 0, jump down, and then we're back at 0 over here. So 50 Newton meters, which was our maximum torque specification, and we ended up using that 50 Newton meters as the value to maximize the acceleration. And then finally, we can also just look at the equality constraint history, where we started with a value of 0.01, which is higher than the convergence tolerance, and we decrease the value up to iteration 3, and then we increase it until we reach this 0 value over here, which is well in line with what we expect for an equality constraint. Now, once all of that is done, I'm just going to type in over here close all, just to make sure that I closed all of the plots. And now I can focus on the post-processing of the DAP-BC workbench. So I type in plot T, and let's perhaps look at RDD for all time steps, body 1 in the one direction. I can also use Pythagoras over here, so just saying the square root of ax squared plus ay squared. But since we're considering one-dimensional motion, I can also write it in this form and simply consider the maximum acceleration in the x direction, since the kart is only moving from left to right. And I can just close the brackets, hit enter, and over here I can see that I now have the maximum acceleration of 4.03 where I start off, and then at around 2 seconds it seems that I've now plateaued at a value of 0, so now I don't have any acceleration in the system. So this tells me that I should see a constant speed when considering the motion of the kart body itself, and therefore I can now go and just retype or hit the up arrow on my keyboard, and now I can consider the x velocity of the kart as well. If I hit enter over here, I can see that I start at 0, so the kart starts at rest, and then from there I increase the speed up to the point where I've now reached 1.2 meters per second, which is the specification of the kart body. It should reach a maximum speed of 1.2 meters per second. So from 2 to 6 seconds, I now have a a constant speed of 1.2 meters per second, and this is why I also saw the zero acceleration for that region. Okay, and then that should be more or less all of the results that we wanted to consider. I think the other example was just with regards to, let me just check, I think it might have been one of the rotational accelerations of the rear wheel as well. This plot is given over here, but it's not really that important to the kinematics that we wanted to validate in our case. So, but you can go and plot this and make sure that it corresponds to the results that were given in the mind map, or the results that you now generated on your side. But yeah, so now we've done the optimization, we validated that our equality constraints have been met, so we're pretty happy with the result that we got for this problem. Okay, and that was then also the second example that we considered for our optimization study. So before I move on to the last section, are there any questions at this stage? Okay, I don't see any questions under the messages yet. So in that case, I'm just going to move over to section 7 of our mind map, which is then just some concluding remarks pertaining to DAP-BC and dynamic Q. So what we've noticed from the two application examples that we've done, the effectiveness of the dynamic Q optimizer is greatly underpinned by the performance of DAP-BC. So considering the number of design variables that I have in the system, the complexity of the objective functions, complexity of the constraints that I impose on the system, also the discretization of input parameters. So how close am I to the initial conditions when I start my optimization? And then do I have any noise or discontinuities in the data? The more noise or the more discontinuity I have in the data, the less effective the gradient optimization schemes become. The optimizer itself will also have an effect on the solution times, specifically considering the convergence tolerances. If I use too tight a convergence tolerance, it's going to take me either more iterations to converge, or it's going to come to the point where the convergence tolerance is too small based on the step size to actually get a solution, and it's simply going to oscillate in between or around the minima that I want to achieve. Variable ranges and move limits can also have an effect. I need to choose my move limits based on that order of magnitude definition that we had in the dynamic Q guide document. If I use too small a move limit, it means that the dynamic Q optimizer is going to take very small steps, and the further away you are from the optimum design when you start your initial conditions, the more steps it's going to have to take, and the longer it's going to take for the system to run up to convergence. Then the finite difference approach that I use under my grad FCH file also has an effect. Typically, forward and backward difference methods use more or less the same number of function evaluations. However, if I choose to use the central difference method, it's essentially a combination of your forward and backward difference methods, which means it's going to take twice as long to solve the gradient for each design variable and defining the function value for each of those analyses or evaluations. Then I also need to consider the step size and the parameter sensitivities, and this is a bit of an out of scope point for the MSD 780 module. If you're more interested in sensitivity analysis, there are some articles online as well as to how it's run. But in our case, we're not too focused on the sensitivity analysis. We're pretty happy with a step size of 10 to the negative 8, unless it's otherwise stated, of course. So in general, a good balance must be found between the accuracy of your solution and the performance of the optimizer. The finer your tolerances are, the longer you will have to wait to find a solution. All right. And that was just a bit of a conclusion on the examples that we've done, the dynamic Q optimizer, and how it relates to the DAP-BC workbench. Okay, so before I discuss assignment 2, just to give a few pointers over there. Are there any last questions with regards to the content that we've covered? Okay, don't see any questions yet. So in that case, I'm quickly going to jump over to the assignment 2 write-up, which I posted, I think it was end of last week or beginning of this week. And this is now focused around doing some optimization on a multi-body mechanism of your choice. Now you can either use the same mechanism that you did for assignment 1, of course just taking into account the feedback that I gave on your assignment 1 report as well, or you can choose a new if you want to. But the idea is that you use the provided DAP-BC Dynamic Q Hybrid Workbench revision 01, so this should be available on ClickUp. And you have to both simulate and optimize one or more features of a planar multi-body mechanism of your choice. Now, the mechanism may not be one of the examples for which input files already exist, the same as for assignment 1. The following files need to be submitted. So I'm once again interested in your DAP-BC input files, but then also your FCH, grad FCH, minimizer inputs, and any additional MATLAB files that you have used to your optimization. And then, of course, a PDF report of no longer than 10 pages. Now, for assignment 1, I was a bit more lenient when considering the PDF report. If some of the points that you gave over there were unclear, I would have gone to your MATLAB files and I would have analyzed, let's say, the mechanism that you defined over there more diligently than what you gave in the report. So in the case of assignment 2, this is not going to be the case. I want you to focus on documenting your setup of your mechanism in detail. So I need to understand what type of mechanism you are setting up, and you need to give clear results, clear and concise results, and good interpretation. My primary focus for the second assignment is going to be on grading the PDF report. So make sure that your report is well documented. Okay, and then just with regards to the hand-in details, assignment 2's hand-in deadline is then Friday, 21 November. And this is fairly close to our exam date, which is then on the 26th of November. So I'm going to mark on the Saturday and Sunday so that you can have your marks back at the latest on Sunday. And you can use the feedback over there to then also prepare for the exam. Okay, so just going over then to the rubric, it looks more or less the same as what you had for assignment 1, but I do have a few additional pointers that I just want to give you over here as well. Once again, mechanism complexity. I'm interested in seeing an advanced mechanism, so an actual complex multi-body mechanism consisting of 4 or more bodies and or links and utilizing different joints. So I don't just want to see revolute joints in the system. I do want to see some different joints being used in the system to just increase the complexity of the problem as well and help you to also realize the usefulness of the DAP-BC workbench. Then for the evaluation of the performed dynamic analysis, you presented both kinematics and dynamics in your analysis with a clear application and evaluation of both. So how does this then pertain to the optimization that you're going to perform? This does not mean that you necessarily have to do an optimization on both the kinematics and the dynamics of the system. So let's say considering both the speed and the torque that is being applied to the system. What I'm more interested in is, let's say in the case of, let's use the cart that we just did as an example. In this case, we only optimized on the kinematics. So we only maximized the acceleration of the system. But once you found your optimum design or your optimized solution, then I want you to go one step further and just consider, let's say, the reaction forces in the system as well. And see, well, if I now have a maximum acceleration, what is the reaction forces at the revolute joints at the wheels? And how does this compare to the initial design that I gave in? Just to have some comparison between an initial design and the final design. Then for the interpretation and the validation of the results. Once again, it should be an in-depth interpretation of the results with many visualizations and critical discussions. The student also provides validation or sanity checks for his or her simulation and optimization results. Now, to better discuss this point, I just want to go back over here and remind you that for assignment 2, you need to simulate and optimize one or more features of a planar multi-body mechanism of your choice. So you can choose if you want to use a single design variable or multiple design variables in your system. Regardless of that, my focus in this case will be more on validation of the optimization that you performed. So if you want to, a good validation would be to say, well, let's start with a single design variable. If I have a single design variable, I can actually go and set up just a linear graph of saying, well, the design variable ranges from, let's say, 0 to 100. So what is the objective function value? So you just generate a plot, let's say, with 100 steps, and you evaluate the objective function at each of those points. And then you perform the optimization and see if the results that you got from the optimization correspond to the maximum objective function that you found from your manual graph that you plotted. So that's one way to do it. The other way is what we just did for the cart example. In that case, we had an equality constraint that we specified on the system. The maximum speed should be 1.2 meters per second. So what I did over there, I performed the optimization. I saw what the equality constraint value at the end was. And then I went one step further. I plotted the speed of the cart versus time, and I saw that, well, it indeed follows the 1.2 meters per second rule. After 2 seconds, I saw a 1.2 meters per second maximum speed being reached. So in that case, you then relate the optimization outputs that you got to your DAP-BC graphs that you get. And that also allows you to perform a sort of validation over there. So in assignment 2, it's not necessarily that you have to perform the validations as you did for assignment 1. My focus over here is just that you make sure that your optimized results correspond to what you expect to get out of the system. Okay, and that is then the last 40 marks of the rubric that will be presented over here. Okay, let's see. I think we have a question over here as well. All right, so Mr. Govender, to confirm, may we use our mechanism from assignment 1? Yes, you're more than welcome to use that. Is MSC Adams in the exam? So at this stage, I am still contemplating on whether it's going to be in the exam. If it's going to be in the exam, it's not going to be, how can I say, you don't have to set up a multi-body mechanism. It will be short questions. So questions that I extract from the lecture slides of the guest lectures. Just to make you a bit more familiar with the Adams environment and just to make sure that you understand some of the pointers that were given over there. But it will be under the short questions rather than long questions. All right, but with regards to the exam as well, closer to the time, I will post an announcement just to give you a breakdown of where all of the marks will go for each question, what will be included. But for now, just know that the exam will be open book, so you'll have access to the PMD textbook, you'll have access to the lecture material, the DAP-BC and the DAP-BC Dynamic Queue workbenches will be made available to you. You'll essentially have everything that you have available on ClickUp at the moment. And then I will also post, I think it was 2 years back, the exam paper over there. Just to give you an idea as well of how we set up the exam. So then you can work through the exam in your own time. I also did a lecture recording last year where I went through the exam paper. So feel free to use that to also prepare for the exam. But other than that, I think everything else will be posted online before your, or posted on ClickUp before your exam so that you have enough information on what to expect. Okay, and I think that then also concludes everything that we wanted to, or everything that I wanted to say about assignment 2. And then that is also our last lecture. So I think if there are no other questions, then I will see you in the exam. All the best with the exam preps as well. And yeah, if you have any questions in the meantime, feel free to pop me an email and I will get back to you as soon as possible. But other than that, thank you very much for this year's session and wishing you all the best with the exams. Thank you very much.